Carbon fiber composites handle tension beautifully, but if you apply heavy longitudinal compression, they tend to fail prematurely. The primary driver of this compressive failure is a mechanism known as fiber kinking. Kinking occurs because microscopic imperfections, specifically random fiber packing and local waviness, weaken the internal structure, prompting the fibers to buckle under load. Historically, micromechanical simulations have tried to predict this failure using idealized representative volume elements, or RVEs. They assume a perfectly straight hexagonal fiber grid, or at best, homogeneous sinusoidal waves. To accurately capture real kinking mechanisms, a model requires statistical scale fidelity. You need a geometry measuring at least 1.5 millimeters in length, containing thousands of individual fibers. When we examine X-ray computed tomography, or XCT scans, we do not see perfect grids. We see a chaotic distribution of resin-rich zones, varying interfiber distances, and clustered misalignments. Therefore, structurally accurate geometric realism is a strict prerequisite. Without representing the actual variability of the fibers, it is impossible to predict how a composite will fail under compression. The standard approach for finite element analysis is to discretize both the carbon fibers and the surrounding polymer matrix using 3D continuum solid elements. Applying this 3D meshing strategy to a statistically representative volume causes the degrees of freedom to scale exponentially, often reaching into the hundreds of millions. Solving the complex mathematical burden of longitudinal compression, specifically the characteristic snapback response where the material suddenly loses load-bearing capacity, can take weeks of compute time, even for very small models. Researchers often try shrinking the RVE to save time. However, this introduces artificial boundary effects that cause the entire model to exhibit spurious global buckling rather than localized kinking. A small, truncated volume will unnaturally twist and contort at its boundaries, failing to replicate the stable, natural kink band formation that larger RVEs can capture. Adhering to elemental 3D fidelity is a strict computational bottleneck. It prevents us from modeling the scale necessary to study actual microstructural defects. Using direct XCT scan data for large-scale analysis is prohibitive. The scans are expensive to produce, limited in physical volume, and lack the parameterization needed to systematically test different architectural variables. The solution is procedural generation. We can use rigid body dynamics to digitally pack thousands of fibers into dense, mathematically controlled bundles. This image shows the limits of the hardcore model, where older packing algorithms like sequential absorption struggle at high densities. They hit a jamming limit very early, leaving the volume saturated with no room for new fibers. Modern workflows solve this using physics engines, such as Blender's rigid body dynamics, which applies simulated repulsion to prevent any fiber interpenetration. As the simulation runs, fibers act as physical cylinders. They shift and lock together into dense, non-overlapping distributions. This repulsion technique drives the volume fraction up to 60. We achieve this by driving the longitudinal fiber paths with 3D continuous noise functions. This visual shows a grayscale noise slice overlaid with red curl vectors. This divergence-free curl noise field guarantees trajectories remain continuous. Straight fibers are extruded through this vector field, inducing stochastic waviness along the entire longitudinal path. Looking at this projection colored by the angle to the z-axis, we can identify the specific distribution of local misalignment throughout the cross-section. In this detailed view, we can identify concentrated orange and red clusters. These represent pockets of high-angle misalignment, mimicking the clustered defects found in actual manufactured composites. These procedurally generated volumes must be validated against real-world data, specifically experimental XCT scans of physical Airtex composite samples. These overlapping histograms compare the statistical inclination angle distributions. The generated model closely tracks the physical Airtex sample, proving the algorithm accurately replicates natural alignment patterns. And this final histogram compares the fiber tortuosity. Again, the generated results accurately mirror the length ratios and waviness found in the physical material. These curl noise pipelines provide exactly what 3D scans cannot: mathematically precise, highly parameterized, and statistically representative microstructures ready for simulation. We now have massive procedural geometries, but attempting to mesh them with traditional 3D solid elements remains computationally impossible. The solution is a physics-preserving dimensionality reduction, known as the shell beam or SB methodology. First, we eliminate the 3D solid elements for the fibers. We replace them with 1D Timoshenko beams, leaving only a single central axis line. Timoshenko beam theory explicitly accounts for the compression, bending, and transverse shear deformations that occur during a physical kinking event, meaning we drop the geometric dimensions while retaining the mechanical physics. Next, we replace the massive 3D matrix using 2D shell elements that dynamically link neighboring fibers. The process starts by calculating a Delaunay triangulation network across the cross-section, establishing a geometric web connecting the centers of every neighboring beam. The edges of this 2D network are extruded along the wavy fiber paths, creating interlinking quadrilateral surfaces. These 2D shells represent the surrounding resin matrix, providing the critical shear support that resists fiber buckling under compression. This shell beam dimensionality reduction drastically shrinks the total degrees of freedom, capturing the exact kinematics of mechanical failure at a fraction of the computational cost. The performance gains from this methodology are absolute. The shell beam pipeline reduces total simulation time by over 99.9% compared to conventional 3D models. Calculations that previously required 2 weeks of compute time can now be resolved in minutes. This speed maintains precision, yielding 94% accuracy for compressive strength and 97% for predicting kinking direction. When longitudinal compression is applied, the shell beam elements accurately buckle and shear, correctly replicating the localized formation of the structural kink band. By eliminating the computational bottleneck, engineers can simulate RVEs containing thousands of fibers, directly bridging the gap between microscopic manufacturing defects and macroscopic material failure. Simulating realistic composite failure no longer requires brute force computational power. It relies on an elegant mathematical abstraction scaling to meet the reality of the material.